the chemistry behind nuclear bombs this week. This is a presentation for Doane University for the General Chemistry 2. Just a little introduction. This is an educational presentation only for General Chemistry 2 at Doane University with Dr. Ken Capps. We're going to go over the atomic bombs and the hydrogen bombs and some of the chemistry behind them. We're going to take a quick review of the isotopes that create some of these bombs and the aftermath that can happen with some of these bombs. Quick overview. Nuclear arms are weapons of mass destruction that use nuclear energy to create an explosion. They're obtained in atomic nuclei and released during nuclear reactions and through radioactive decay as well. The atomic bomb usually looks like a torpedo. Inside, a nuclear reaction occurs. This is a chain reaction of the fission of heavy nuclei. Only certain elements are capable of a heavy reaction. Most commonly is uranium-235, which is radioactive, and there are also different isotopes of uranium, like uranium-238 as well as uranium-234. These different numbers refer to the different isotopes, and they are shown here as well. They also need to be, uranium-235 needs to be at 80%, so enrichment of the uranium is needed when creating these atomic bombs. If uranium is not a possibility, plutonium-239 can also be used. However, it's rarely found in nature, so it would need to be created artificially, which would be a major task to undertake. Let's see the chemistry behind atomic bombs. So there's a mass of fissile material that is concentrated in one place. This is also called critical mass. When this is reached, a nuclear decay reaction occurs. This in turn releases a lot of energy. One critical mass is not enough for a large-scale bomb. Several, usually 4 to 5, would be needed in order to have a truly destructive bomb. In order to achieve this, we use implosion. So if we look at the bottom picture here, we have a guided explosion on the outside that sends these separate masses together, and this in turn increases the density of the uranium or plutonium in the center here, which creates the critical masses needed for the larger nuclear explosion. With our hydrogen bomb, here energy is released due to thermonuclear fission. This is a very fast explosive reaction that occurs inside the charge with the help of elements like deuterium and tritium. Other heavy elements used, mainly of which is lithium hydride. By itself, this does not create an explosion. There needs to be a detonation by an integrated nuclear device. When activated, energy is released which triggers an explosive thermonuclear reaction inside the bomb. It's a little scary to think, but theoretically there is no limit to the power of these hydrogen bombs. So hopefully that doesn't come to it, but yeah. The aftermath would be some shock wave, a little bit of light radiation, and other forms of radiation. This radiation is a result of the explosion of the nuclear weapons, more specifically the hydrogen bombs that we were talking about. And there are three types of these ionizing radiation. We have alpha, beta and gamma radiations that would contaminate the area surrounding where a nuclear bomb was set off. The alpha radiation does not do much harm, and sometimes our clothing would protect us against this type of radiation because it doesn't penetrate. However, we would want to try to protect mucous membranes, as it could affect the mucous membranes. There is also beta radiation, which becomes a little more serious and can cause burns and cataracts, and is usually seen at a closer distance from the nuclear explosion. And then the most dangerous we have is gamma radiation, which is hard to protect against because of its high penetration. So you'd need some type of lead or concrete to truly create a barrier. And this penetration causes internal damage, which in turn could cause radiation sickness, cancer, and even gene mutations.